Hello and welcome to the Homeland Defense and Security Information Analysis Center webinar titled NASA's X-57 Maxwell All-Electric Aircraft. My name is Steve Rutherford and I'm the Director of the Homeland Defense and Security Information Analysis Center, and today we have the privilege of hosting Mr. Sean Clark for this presentation. First, I'd like to thank our sponsor, the Defense Technical Information Center. The HDIAC mission is to collect, synthesize, produce, and disseminate scientific and technical information to the DoD and federal government users, and this webinar is made possible through DTIC sponsorship. I'd also like to thank all of you all for taking time out to join us today during these challenging times. A few housekeeping notes as we begin. Please note that all lines have been muted. If you have questions during the webinar, they can be submitted using the attendee chat box on the left-hand side of the screen. We're going to work to save the last 10 minutes or so of the presentation to go over those questions and discuss them. However, if we run out of time, we'll make note of all remaining questions and post responses after the conclusion of the brief. Please also note that this webinar is being recorded. So a link for the recording as well as the slides will be available at our website, www.hdIAC.org, for later download. With that, it is my distinct pleasure to introduce you to today's presenter, Mr. Sean Clark. Sean is a Senior Research Systems Development Engineer at NASA's Armstrong Flight Research Center. He is the Principal Investigator for NASA's X-57 Maxwell Aircraft Electric Propulsion Technology Demonstrator, and a member of NASA's Electrical Power Systems Capability Leadership Team. Before joining NASA, Mr. Clark was a Senior Operations Engineer at several U.S. Bureau of Reclamation hydroelectric power plants. He earned his Bachelor of Science in Electrical Engineering at the University of Florida, Gainesville. Sean, the floor is yours.
Thank you so much, and thanks for having me. I'm really excited to share the work we're doing on the NASA X-57 project with you guys. So the X-57 is NASA's first piloted, inhabited X-plane in about 20 years. We've had a lot of experience with X-plane research programs over the years, and we've got a couple partnerships with the DoD right now, including X-56. But this is a return to putting test pilots in the seat at NASA. So it's really exciting, and we're really excited to bring the new electric propulsion technologies into flight with some of our research. So I've got a lot of slides here. I'm going to talk a little bit about the technology that we're using in order to enable this new aircraft capability and some of the potential impacts it can have in the marketplace and in other vehicle segments as well. And I'm looking forward to your questions. So why are we here? Where did we start? The X-57 program basically kicked off out of an interest in distributed propulsion. And distributed propulsion, we're using kind of an interesting definition for that. We're studying how we can take the propulsion technologies, the electric motors and propellers in this case, and put them on the aircraft in a way that fundamentally changes the way you can design the aircraft. It either brings specific benefits to aircraft systems or enables new aerodynamic performance or something along those lines where the electric propulsion system gives the aerospace designers a new tool for aircraft layout. This example here on the right on this slide of the P-59 and the P-63 is kind of interesting. There's a couple lessons you could take from this. The jet age hadn't quite arrived in 1942 when these two airframes were designed and first flown. The P-59 had these fancy new jet engines, but didn't get much better range, didn't get much better performance. Used a lot more fuel than the more traditional piston engine platform with the P-63, and the U.S. didn't end up buying very many P-59s. But that technology did grow out into a whole new industry. This was one of the first turbine aircraft that the U.S. Air Force had started to use. And so the initial rollout doesn't always look like the most optimal application, and it's very important to size your propulsion technology to your mission and to your airframe. And it could grow into something. And that's what we're seeing with the electric propulsion technologies as well. Click the slide. There we go. So the X-57 Maxwell is using electric propulsion technologies instead of piston or turbine engines. In order to make the six-plane as affordable as possible and get as much research done in the budget that we have, we're actually basing it on an off-the-shelf GA airplane, a Tecnam P2006T. This is a four-seat airplane. It's an Italian design from the Tecnam company. It's got a gross takeoff weight of about 2,700 pounds. We're actually increasing that a bit for some of the technologies that we're using with some NASA airworthiness analyses. But it's got a pretty good internal volume, and it's got a high wing, so it's an ideal test bed for these types of technologies that I'll be showing you over the next 30 or 40 minutes. One of the things we're trying to do with the X-57 project is raise the technology readiness of electric propulsion technologies in general. So the electric motors, the inverters, the battery systems needed to power these things. There are early versions of this technology in the marketplace already, but in order to start to roll this out to mass market where the public will be exposed to it, we'd like to help make sure that the industry is able to retire technology risks and do this in a safe way. So that's one of the main goals of X-57, is to share the design and airworthiness process that we're following at NASA in order to help kickstart the commercial industry and help support the FAA as they're starting to certify these vehicles. It's a pretty distributed project, X-57. So I'm calling from California. I work at NASA Armstrong Flight Research Center in Southern California. We've got a lot of design partnership from NASA Langley, when a lot of our main aircraft design team is out in Virginia. And then a lot of our analysis team is at NASA Glenn in Ohio. So it's a multi-center partnership between the NASA research centers. We also have heavy participation from small businesses. So a lot of the work, all of the integration work is being done on a small business innovative research contract. And the prime contractor is Empirical Systems Aerospace out in San Luis Obispo, California. And they've let subcontracts out to many other small businesses across the country. So just to step through a couple of them, Scaled Composites, you may have heard of, is an airframer nearby here in the Mojave Desert. And they did the integration of the electric propulsion technologies in our initial phase. Joby Aviation designed our cruise motors and our cruise motor controllers, and I'll be talking a lot more about those. Zone 5 designed our new high-performance wing that I'll be telling you about. So it's an all-composite wing with a very high aspect ratio. Or I'm sorry, that's experimental. And then Zone 5 did is in the middle of doing our design for our new high-lift motor system, which is our highly distributed propulsion augmentation device. Battery technology turned out to be a challenge for this project that we had expected was already retired in the marketplace, but we ended up putting a lot of research into it. So I'll show you some of the progress we made there, and that's been in partnership with ESAero and Electric Power Systems. And then TMC Technologies is our software validation site out in West Virginia, along with Tecnam, the airframer that I mentioned earlier. So electric propulsion technologies are really exciting. One of the things that you've got to decide when you start to roll out these new technologies is what benefit are you looking for? On this airframe, we decided to pursue a cruise performance benefit. So what our designers at Langley did is they started with a traditional wing and bounded by the wingspan and footprint of the original Technum, and tried to optimize that wing for the cruise condition, for high-speed cruise. And so when you do that, you're able to get a lot of the benefit just by shifting the L over D curve to the right on our diagram here, so that the actual operating point of the aircraft is much closer to the peak performance point of the wing. So that's kind of low-hanging fruit and not too revolutionary. But one of the other things we did with that wing is we optimized the airfoil to take advantage of putting our propulsion system at the wingtip. And so by integrating these lightweight, reliable electric motors at the wingtips, we're able to directly impact the vortex drag that normally forms there. And so that's a key optimization constraint on the airfoil itself. And so that gets us another increment in cruise efficiency. The other challenge, though, is when you optimize the wing like this for cruise, we've got such small wing area that takeoff and landing speeds are greatly impacted. And so the stock aircraft has a stall speed of something like 62 knots. Our new wing would have a stall speed of in the neighborhood of 80 knots if we didn't do anything else. But that's where we've introduced a high lift system, also using electric propulsion, using some other electric motors that I'll tell you a little bit about. And that system actually, at low speed flight, is able to recover that low speed performance on the wing, even though it's a very small wing area. So that's a critical technology benefit from the system. Let me make sure I've covered everything there. One other note from this chart that's kind of interesting as well is the installed benefit of the propulsion or the installed impact of the propulsion is actually a benefit on our new wing. So the solid lines are the unpowered performance. So the original wing in black and the new wing in blue. When you install the propulsion system, the wing performance is compromised a little bit because of the way the propeller interacts with the airfoil. With our new wing, because we've got that vortex disruption effect from the wingtip mounted propulsion, we're actually able to see an improvement in the aerodynamic performance of the wing because we've designed the wing to take advantage of that. And so we actually get a slight increase in wing performance depending on the operating condition. So it's a really exciting technology. It's unproven, so we're hoping to evaluate that during flight tests of the X-57. I mentioned it was a much smaller wing, so we're trying to be fair and keep our new wing in the footprint of the original wing. And that gets tricky when you got your new propellers mounted all the way out the wingtip. So we actually pulled the wing in a little bit more just so that the entire footprint is within the original wing. So on this picture here, you can see the blue outline is a stock Technum P2006T with a 37-foot wingspan. And the gray wing is the new high-performance wing that we've designed with the primary propulsion out at the wingtips and then our distributed high-lift propulsion spread out along the wing. So that's what the 12 small pods are spread along the wing. So the total area reduction, we're at about 40% of the original wing size. And that really just comes down to optimizing it for that cruise condition. So a side effect of that cruise optimization is the area reduction leads to a lot less skin friction drag, and so we get some performance benefit directly from that as well. But we also end up with much higher wing loading, which is kind of interesting. So we're expecting that the gust sensitivity for this aircraft will be much lower. We'll have a ride quality that's comparable to much larger aircraft traditionally, whereas if you've ridden in GA aircraft, if you have a weak stomach, you can certainly get knocked around a little bit and find the experience uncomfortable. But it could be that these technologies enable us to improve ride quality as well, even though that wasn't a primary goal. Okay, so I've got a little video here that we'll queue up. This is kind of an interesting description of the way we're phasing the project. If we can get the video going. So we're laying out the project in a phased approach so that we can roll out the technologies in a safe way, because we're putting these propulsion systems at the wingtip of an aircraft, which is a very challenging installation location for your primary propulsion system. So we actually started with what we call Mod 1. So I'll play the first clip of the video here. A little bit slow for me, so hopefully you guys are seeing it. So Mod 1 is basically the traditional aircraft. So if I pause it there, it's using the Rotex 912S engines. They're 100 horsepower each, installed in the Technam designed wing. This is basically an off-the-shelf aircraft. We rented one and instrumented it so that we could get performance data out of it. We measured the fuel flow and added a bunch of aero sensors and flew it around our test range here at Edwards Air Force Base so that we could understand the models that we were building for the baseline comparison of the airframe. And then in Mod 2, it's basically the same aircraft. You can't see the difference, but we've switched out the nacelle for electric motors and motor controllers in place of those Rotax engines. And this is the version of the aircraft we're building right now. So this is in the hangar out at NASA Armstrong on site at Edwards Air Force Base. And we plan to flight test this in about a year. Everything's up in the air right now as we're dealing with current events, but we're in the integration phase and getting ready to go into the full system test and then taxi test and flight test of this Mod 2 configuration. So it's the same wing, but with the electric propulsion system installed. And then one of the bigger technologies here as well is the battery system. So this aircraft is about 300 pounds heavier than the stock aircraft because we've installed our battery system in the back seat and the cargo area. So then the more exciting flights for research come up. So Mod 3 and 4 are actually combined now. Mod 3 is testing the cruise system on our new wing out at the wingtips. And then Mod 4 is that same new wing with that same cruise system at the wingtips, but with the 12 small motors distributed along the wing so that we have this high lift capability in low speed flight. And so that wing has been built and those motors are in design process right now. So I'll tell you a little bit about that as we go through some of the technology slides. So if I say Mod 1, 2, 3, 4, I just wanted you guys to have that up front there so you understand what I'm talking about. Mod 2 is the electric version, and then Mod 3 and 4 is the new research wing with the propulsion at the wingtips and then eventually distributed propulsion. All right, waiting for the slide to show up here. Okay, great. So as I said, we're working on Mod 2 right now. One of the primary motivation for Mod 2 was as I said, raising that TRL level for the electric motors, for the motor inverter system, for the battery system, so that we would have enough confidence to put our test pilot in the air with these systems driving from the wingtips. And so it's a risk reduction phase and allows us to go through an airworthiness process with these new technologies. Some of the new technologies that are critical have some impact in the marketplace already. There are some experimental electric aircraft in the U.S. market that are using batteries. There's a few more certification routes in Europe right now, but setting the battery standards for piloted aircraft, for inhabited aircraft is a pretty critical activity for us. And so feeding back to the regulators what we're learning about the battery safety trades that manufacturers will have to make is pretty critical. So this has turned into a pathfinder for that regulation approach. Even though NASA is a self-certifying agency, we do our own airworthiness certification for our research aircraft. It's analogous to what the FAA would do in the commercial sector, and so we're hoping that we can help the FAA leverage a lot of the experience we're having and understand some of the risks and hazards that we're working through. So that's been a nice early benefit from the Mod 2 phase of the project. So in Mod 2, we've got a few technologies rolling out. One is the cruise motors themselves. So when we started the project a few years ago, we didn't really have anything in the marketplace that we could just drop in to the vehicle design at our operating point. So we ended up doing a design effort with Joby Aviation, who's been designing comparable motors for similar applications over the last few years, and they're actually going on to spin that into their own platform that they're hoping to bring to market in the coming years. We had to establish new test standards for cruise motors. So the FARs, the regulations for certifying power plants on aircraft, didn't have any provisions for electric motor certification. And so we had to read between the lines on FAR 33 on how you would certify a piston or a turbine engine and come up with a certification approach that would make sense for electric motors and make sure that not only were we not over-testing with certification steps that are specific to fuel burning engines, but also not missing any tests that would be critical to new screening that would be needed for electric motors. We're also working through maintenance standards for our electric motors. So this is a new technology, and we've got highly skilled aircraft electricians and mechanics on our aircraft that need to know how do they ensure that the aircraft is ready for operations the next day. What parameters on the aircraft do they need to be watching in order to make sure that the technology is reliable enough for another flight. We've had some challenges directly with these motors. So the motor design that we worked through with Joby is it's fully air cooled and it's direct drive. So there's some challenges there for an electric motor design perspective because it's a very low speed electric machine. It's also so direct drives, there's no gearbox. We wanted to make sure that there was very few moving parts so that we could work through the failure modes on our lightweight project without having a lot of redundancy needed and working through the failures that would be potential from a gearbox. So this design's actually been published. Joby wrote a nice paper and published it in the AIAA Aviation Forum in 2017 and steps through how they optimized the footprint of the motor, the mass and volume allocation we gave them to meet the requirements, and how you design an electric motor with those kind of constraints. And so that was a really nice research product from this work. We did find that as you build these technologies and put them into a flight line environment, that some of the design techniques and fabrication techniques that they were using were insufficient for that new environment. And so some of the crimps, some of the interconnects between the motors, some of the way that the motor mounts to the aircraft, we had to go back and do another design iteration that we're just wrapping up now. So it's been a really interesting experience, and we're really happy to be able to learn those lessons before flight, and it's a testament to the screening program that we've put in place that we've been able to get those design improvements made early on. Let me skip here. So coupled with the motor design is the motor controller design. So this is an inverter system that takes the DC power from the batteries and turns it into AC waveforms, basically, that go into the electric motor. And it's a pretty critical piece of technology because it needs to be able to handle the full speed and voltage range of the power bus, but also needs to be able to respond to the pilot command as he moves the throttle levers around. And so it's a pretty complex electronic device. We're actually using silicon carbide MOSFETs, which are high band gap switches. Basically, they enable us to chop up the DC power into the EC waveform very efficiently, which is critical when you've got the such high power applications. So this box is about 20 inches long by 1.5 inches by about 6 inches or so. And it's capable of converting up to 80 kilowatts of power. And so getting that level of power conversion with high enough efficiency that the rejected heat doesn't disrupt the entire process is a pretty critical challenge. And the silicon carbide technology is absolutely essential for that. We wouldn't be able to do this with traditional MOSFETs. So that's been an area of intense research. We're also developing this as a level 1 safety rated software so that we have absolute assurance that when the pilot asks for a level of torque from the motor, this system will understand that, make the right choices, and make sure that the motor forces are appropriate and not apply forces when it shouldn't and not fail to apply forces when it should. So that's been another area of intense development. We're actually rewriting some of the executive software in-house at NASA just to make sure that we've got absolute understanding of every state and phase of the software path so that we're able to certify it to that highest level of airworthiness that NASA has. Similar to the motors, I've got a slide here on technology challenges that we've overcome. So packaging all of this 80 kilowatt conversion into this little box has been a big challenge. We're moving a lot of volts and amps through here, and making sure we've got the right clearance to handle that as everything gets closed up has been a bit of a challenge. And you can see in this picture on the top right, we actually had some marking from our DC link board up to our AC bus bar board. And so it was a lesson in design techniques for these types of applications. Since then, we've actually even discovered some more failures in the silicon carbide MOSFETs themselves. So this has been pretty critical. When this design was done in 2017, the state of the art for MOSFET modules, there was a first generation out from the major solid state electronics manufacturers. And as we went through the formal thermal and vibration testing to make these boxes ready for flight testing this year, we started to find failures in our MOSFETs that were related to the vibration environment. And so it turns out this first generation MOSFET was not able to withstand the flight environment, and actually a pretty benign flight environment that we had simulated on our vibration table. And so we went through a lot of design revision and study, and we took apart a lot of these MOSFET modules and studied the way that the dies were mechanically mounted and tried to make sure that there wasn't a fundamental design flaw with the technology. And the conclusion is that the packaging of these silicon carbide MOSFETs has improved quite a bit over the years. The original generation just was not laid out in a way that would be robust for flight applications. They always worked great during our ground test events and when sitting on a bench, but when we started to put them in application where they needed to be a little bit more rugged, they were just not appropriate. So we're in the process of retesting with a later generation model that seems to be passing all of our initial testing. We've been able to put it through our vibration and protovibe qualification testing, and proven that our replacement modules that are a little bit more mature technology have been working really well. So we're right on the cutting edge of this technology, but it's been quite a challenge. One thing I'll point out, I see a question in the chat. The redundancy of the system is pretty critical to this technology as well. So we've got 2 motors on the aircraft, and in Mod 3 and 4, those are going to be installed at the wingtips. And so that's a pretty critical application. And someday these technologies, I strongly believe, will be reliable enough that will be an appropriate location. I wouldn't put anyone but a high-performance test pilot in an aircraft like that right now. But that's why we're doing this research, in order to help raise the readiness and reliability of this technology. In order to help round that corner a little bit, we've actually built our motors with as 2 3-phase motors. They have 6 phases wired in instead of a single 3-phase motor. And that way we're able to use one of these inverters for each set of 3 phases. And so we basically have 2 isolated powertrains from 2 separate batteries through 2 separate power transmission lines through the wing to 2 separate inverters into 2 separate motor windings before they drive the same mechanical rotor. So that's a really key redundancy capability it's not uncommon in the marketplace. It's starting to get out there a little bit more, but it's absolutely essential when you start to put these technologies in critical locations like the wingtip. So I mentioned batteries earlier. We had expected when we started the project that with looking around, especially in California, there were so many electric cars out on the roads that battery technology would be ready for this type of experiment. And we're really researching motor and wing design options, and didn't really expect to have to do a lot of research into battery development. So we spec'd out a battery system with a moderate energy density. We set aside, I think it was originally about 690 pounds, and we overshot that a little bit. So our battery system's at about 860 pounds. And that provides us with 54 kilowatt hours nameplate, which means we can rely on about 47 kilowatt hours of available energy when you take into account depth of discharge limits and degradation over time. And that includes a 30% packaging overhead, which is fairly aggressive, actually. Normally, for the types of safety requirements that I'll talk to you about, you'd need a lot more packaging to encase the batteries, but we're able to do that with only, so for every pound of lithium cells, we've got another 1/3 of a pound of aluminum and hardware around it. Thermal management has been a challenge. So everything on this aircraft is air cooled, the battery system included. We're actually planning to chill our batteries before flight, so that as they warm up throughout the operation, they stay in the ideal operating range and have high performance, but also don't get anywhere near the thermal runaway thresholds that I'll talk to you about. Battery management software is another critical technology. So we really need to understand the state of the batteries, the health of the batteries. This has been something that can be confusing if you're a new electric aircraft owner in the marketplace. Is how full is your fuel tank? It's a little bit worse than in an electric car, where it might say you've got 100 miles range left, and then a minute later say you're down to 80 miles range because you're using the accelerator a little bit more. Those effects are amplified for aircraft, because you can go from almost no power in a descent to much more than standard cruise power in a climb. And so understanding how much energy is left in the tank is really critical human factors feature that we're hoping to understand as we go through this and really study the state of charge algorithms in the battery system. So as I mentioned, there was no off-the-shelf battery system available to us. What we ended up designing was with Electric Power Systems, which was a new company at the time, and DSR, our prime contractor. We designed a box shown here that's about 100 pounds. It would hold about 640 of these 18650 cells. So if you haven't seen these are cylindrical cells. They're shaped kind of like a AA cell, but they're about 30% longer and 30% larger diameter, and they're lithium. So they're different lithium chemistries, different anode-cathode combinations to get different energy density and thermal properties. So we were able to fit about 640 of those, and each one of them stores about 3 amp hours. So if I go to the next slide, I've got a video of a thermal runaway test that we did. So I'll set that up for you for a second. The thermal runaway test is a test to make sure that if any one cell has a design flaw, has a manufacturing defect inside the cell where it develops an internal short, and that can happen well after acceptance testing. This could happen in the middle of a flight campaign because the way these internal pieces of FOD will migrate around as the lithium ions move around. It's kind of unpredictable. So you really needed to plan for individual cells having a failure. But we want to make sure that if a cell has a failure, that the neighboring 18650 cell doesn't also have a failure, because then that turns into a cascade where you've got one triggering the next, and it's critical that doesn't happen, because being able to contain a failure of that size is totally challenging. So let's see if we can cue up this video. This is a test we did. This had about 320 cells installed. So it was half populated. The box weighed a little over 50 pounds, even though it was our 100-pound box. We did this out at a test site in New Mexico, just to contain whatever event would happen in case that the propagation wasn't prevented. So I'll go ahead and play, and I won't talk because there's a lot of sound on this. So I'll pause it and point out some things there, see if I can get the video to back up. So we didn't contain the propagation event, as you can see. The initial cell, we were heating it with nichrome wire, basically toaster wire wrapped around one of the cells, and it went into thermal runaway and caused the neighboring cells. There we go. And ended up having that chain reaction happen over about 5 hours. We had to go to lunch and wait for it to burn itself out while we left the cameras going and left the techs standing by, because it was just a total failure of the propagation prevention technology. So thanks, John. If we can go back to the slides. The result of this was we had to go back and redesign the technology from the ground up, basically. So if I go to the next slide, we actually started using what the state of the art was from NASA research that we were doing for the space station. So NASA designs our own batteries for the space station itself, and then also the astronaut EVA suits. And the astronauts have these multi-tools that are kind of like a cordless drill that they use during EVAs, and those are custom batteries that are built up from these 18650 cells as well. So the picture in the top left is a test cell for the latest generation of those NASA batteries, and you can see the 18650 cylindrical cells embedded in an aluminum block. Basically, we have this interstitial substrate where we can install each of the cells. and put very small gaps. The block walls between the closest points in the cells is as small as, I think it's about 0.4 millimeters. And so the putting that technology in place for this battery allows for any one of those cylindrical cells to have an internal failure from a manufacturing defect or from a workmanship closeout defect or from an assembly defect, whatever it is, and prevents it from spreading to adjacent cells. Because that aluminum wall, not only does it shield the initial event where there could be flame or hot electrolytes escaping from the cell, but it also distributes the heat. And so that turns out to be a key technology from the NASA research that we've done down at Johnson Space Center, is by making sure that the cells are able to reject their heat into the rest of the pack and spread that heat thinly enough that the neighboring cells don't, any one individually, get over a thermal threshold. We're able to make this technology work in a safe way. So that's been really critical. So what EPS did is they took that design technique and built test cells, test units, like in the bottom left picture there, and triggered cells into Runaway over and over, and eventually came up with a design where they were able to use a heater cartridge that had the same temperature profile. So that was a really useful design technique to get it to go faster. And then eventually, once we got all of the packaging figured out at that subcell level that holds 20 cells, we're able to build that up into our modules. And our modules are now designed for 160 cells each, so that you can see them mocked up in the aircraft on the bottom right, and then the initial test run of modules is in the top right. And so they're about 51 pounds each, and they hold 160 of these 18650 cells that are 3 amp hours each. And each one has a terminal voltage of as much as about 60 volts. So they're something that we can handle. Our techs can move them into the aircraft at 60 pounds. It's reasonable to mount it in the aircraft. And it's also a small enough package that we can handle the thermal loads on the skin without having to worry about any one cell triggering its neighbors into thermal runaway. So if I switch to the next slide here. This is the new design. We did another test at our new test facility that EPS built up in Utah. They're actually up in northern Utah at the university there. This is, I have a video of this. You can't see anything moving, so there's not really any point in showing it. But on the thermal camera, you can see what happens when we trigger. The worst case cells are always the ones in the corner because they have the fewest neighbors and the least opportunity to reject heat to the rest of the pack. But we're able to put dummy cells in those corners that we can artificially trigger into a runaway, and when they go into runaway, verify that all the neighboring cells don't also go into runaway. They're still able to hold a charge. You wouldn't obviously want to use the battery after that, but it didn't have a runaway event. We didn't see any smoke or fire. We saw this heat on the surface with the thermal camera, but that was all you could see in the room at the time. There's no noise, no sparks. It was a huge improvement. So that's one of the technologies that I think is really critical for the private sector as well. Is there are not a lot of batteries in the marketplace that have this feature where the runaway event is prevented from one cell to another. And if you're not going to be able to prove that, then a certification package is going to have to show that the worst case runaway event that is credible, if that means all the cells in an enclosure go into runaway, that needs to be contained in an aircraft so that fireball doesn't escape into the aircraft. And if you're doing that for more than a few dozen cells, it gets really intractable because there's so much energy in these lithium cells. We're using lithium NMC, nickel manganese cobalt electrolyte, which is kind of middle of the road energy density. Lithium polymer lipo cells that you might see on like hobby grade aircraft, have even more energy density. And so if you're really going to pack these cells into an aircraft, you need to have a containment system that's matched to your worst case failure. And if your containment system is going to be less than thousands of pounds, then you need to find a way to exclude propagation failure. So that's kind of the conclusion of our battery research. So just to wrap up, I'll go through a couple other technologies real quick. The electric propulsion system is highly complex. We're going to end up with 14 motors on this aircraft, and actually 16 motor controllers on this aircraft. And so we need to be able to give the pilot information about his vehicle without overwhelming him. And so a lot of the displays we're developing will be very interesting and should help in the marketplace. We're actually using some of the design techniques that Pipistrel uses, which is a small Slovenian company that's been building electric airplanes for several years. And we actually are cooperating with them a little bit on the display design techniques. So that's a nice opportunity for collaboration as well. Quick update on the Mod 2 vehicle. This is out at NASA now. This was at Scales Composites until last summer, and then we delivered it out to NASA, and we're doing the final integration testing before we go into taxi test and flight tests about a year after we're able to get back in there. I think I've covered most of this. I really want to get to a couple other technology pieces. So Mod 3 and 4 is where we've got our high performance wing. And so that's really critical. It's taking all these same technologies that I just described, the motors, the batteries, the motor controllers, and putting them in the really exciting application positions on the aircraft. We do need a new wing for that. So we've got an all-composite wing designed by Experimental and integrated by ESRO out in California. It's a floating spar design where the main spar transfers all the loads through ribs to forward and rear spars that intersect with the fuselage itself. And so it's kind of a complicated load path that's more like a glider wing. So that's a little bit innovative for this type of aircraft, but it allows us to fit all of the power handling and instrumentation and control cables into the wing. So we need to move as much as 250 kilowatts out of our batteries mounted in the fuselage up into the wing nacelles where the motors are. And so we need a lot of volume for wiring there. I mentioned earlier in Mod 1 where we've got a flight sim developed, and this has been critical for us as well. We've got a very nice simulator capability out at NASA Armstrong. Our Langley team is designing the flight sim itself and making sure that the sim physics map to the aircraft performance that we see in the Mod 1 flights and that we see from ground testing with our new propulsion system. And then we put all of that into the piloted sim at Armstrong, so the pilots can get in there multiple times a week and sit down and understand how the technology makes the aircraft behave and how the technology works when it starts to fail. So that's been really critical, is what does the response amplitude need to be if we have a motor failure, if we have a controller failure, if one of our prop pitch controllers fails. The pilots are exceedingly familiar with that even before getting in the airplane itself. And I think my last technology slide here is the motors. I'm waiting for it to update on my screen. I don't know if you could see it yet. Yeah, there we go. So our high lift propulsion system is also a pretty tricky design. We needed this system to augment the airflow over the wing at low speed conditions, but we needed to get out of the way at cruise. And so we have this folding propeller design that enables the uniform flow increase over the wing when we spin up these motors. And then when we stop, the propellers will retract in and snug up against the nacelle so that they're in an actually pretty low drag configuration for cruise. It looks like a pretty messy wing, but because we've mounted the nacelles low on the wing and been able to store these propellers very cleanly, the drag penalty in cruise is actually not that bad. So that's been pretty critical. And we're right around CDR. We had an initial CDR for this design in November, and we have a couple open items that we're still working, so we're going to do a small Delta review in the coming months, and then go into fabrication for this system this summer. So I have one more video to show you just to kind of wrap up and see how the technology all comes together when you put all these systems on the aircraft. So it's kind of it's really exciting because we're able to use electric propulsion technology to really change the way we think about aircraft design. So we end up with this high performance wing that's got a pretty short take. It basically mimics the original GA aircraft, but uses, once you fold up the propellers in flight for the high lift system, we're in about 1/5 the energy usage per mile traveled at cruise that the original aircraft would use. It takes a little bit more energy to climb. It takes a little bit more energy to charge the batteries that I'm not counting when I say 1/5, but when you look at the energy that we carry into the air and how much of it we use per mile, it's massive improvement. So it's really exciting. And then the last slide I'll mention just for you guys to bookmark is we've set up a technical portal for this on the nasa.gov slide. So if you go to nasa.gov/X57/technical, we're collecting all the research papers that we've written. We've written close to 100 papers at this point over the last 3 or 4 years, and we've got more coming out every conference season, basically. So those are all going up on our technical portal here, but then we're also starting to publish things like our design reviews. And so we've done a preliminary design review and a critical design review for the overall vehicle system, and we've completed the preliminary design review for our high-lift system, and we're wrapping up the critical design phase there. So those design reviews are basically 1,000 pages of slides describing how all the subsystems work together, are also being published. And then as we go through the airworthiness process, we'll be publishing all the airworthiness artifacts as well. So anything that we can help accelerate industry with, if it's motor test program, or if it's a maintenance plan for an energy converter, or whatever it is, we'd like to get that published up here so that we can help the marketplace take that and really get these technologies into the commercial sector as quickly as possible. So I'm really excited about it, and I think I've got a little time for some questions. Thanks.
Hey, Sean, this is Steve. Again, great job. Thanks again so much for that. That was a great brief. You have a whole passel of questions, so we'll try to get through as many as we can in the next 10 minutes or so. So the first question from Philip, he asks about the choice between power cells and batteries. Power cells offer some distinctive advantages, and batteries have their limitations. What was the rationale behind that choice?
Yeah, it's a pretty tricky optimization there, because even in the battery sector, there's such a wide range in energy density and volumetric specific volume of the cells, and so we ended up with I think what's going to be kind of a universal challenge, where the ratio of how much energy you need to how much power you need is kind of critical. We needed quite a bit of power for takeoff and climb, but you don't need very much power when you're in cruise, but you want to have a long cruise segment. And so you end up with having to compromise between what are called energy cells and what are called power cells. We have kind of a middle of the road cell. We're using the Samsung 30Q cell. If you want to find the data sheet on that, and there's information on our technical portal about it as well. But that cell is pretty good. Samsung's got a really good reputation for manufacturing repeatability, and it also has a reasonable energy density for the package. Something else NASA really likes is the 18650 form factor, and I expect the 27500 form factor is going to be similar as well, but I'm sorry, 26700 form factor, because the cylindrical cells have a nice surface area to volume relationship, where they've got a lot of volume there for energy storage, but then there's also a lot of surface area in order to get that heat out, and that's been a really critical design consideration.
Thanks, Sean. So Lee asks whether you're using an AC bus or a DC bus, and then he asks you to explain a little bit about the grounding scheme for the system.
Oh yeah, this is critical. So, and this has been a bit of a challenge. So we're using a DC bus. We've got our battery system has a terminal voltage as high as 537 volts. It's basically 128 1860 cells in series, and then also parallel. So that bus is isolated from the aircraft, and we have isolation detection on the aircraft. So that way we can tolerate a failure of the bus, a short to the aircraft chassis, if there's only one short. And if we detect it, then we can shut everything down and go fix it. But if there's a second short, we also have protection devices in place. We've got fuses on our system. So grounding is a challenge. We also separately convert that high voltage to avionics power. So we have 13 volt and 28 volt systems on the aircraft, and those are grounded in a more traditional aircraft style. But the high voltage system is floating relative to the aircraft.
So Mike asked about considerations you guys had to make for preventing some sort of electromagnetic interference.
Yeah, and we're expecting to learn more about that if there is a constraint there for us in the system testing, but it hasn't really been a problem for us so far. We do have programs in place at Armstrong to make sure that we're not radiating and putting anyone at risk, and so we do those tests at the bench level and then at the vehicle level. But our choice for the integration approach on the project was to not try to analyze all that ahead of time, because it's a pretty big undertaking. Instead, we've built the systems, and then as we're testing them, we're making sure that the kind of best practices that we're using don't introduce anything, and then we can band-aid it if we have to. And we haven't really had to yet, so that's been good. We've had a couple problems with current sensors getting interference, and we've been able to get hardened current sensors, but overall, we haven't really had much problem with that.
So we had a question come in from one of our YouTube viewers, and he asks, how many cruise motor controllers are there? You know, one per plane, or do you have one per motor? And then there was a follow-on question for one of our AnyMeeting viewers that asked if the CMCs were cooled and how they're cooled.
Yeah, great question. So for the cruise system, it's two sets of windings in each motor that are electrically independent. It's basically two Y-wound motors that are interweaved around each other. So a few of the stator slots are from one inverter, and a few are from the other inverter, and it kind of alternates around the circumference of the motor. And that lets us put independent inverters on each of those Y windings. So that's a really nice design technique that allows us to have a failure in an inverter but not lose that whole motor. And in fact, you could drive the surviving side to even higher power. So there's actually two inverters per cruise motor. On the high lift motors, there's one each, but there's 12 of them. So we can tolerate losing several of those before the pilot really needs to fly the airplane differently. For cooling of the system, everything's air cooled. It is a design simplification, but it also means a thermal complication. So the inverter system for the motors actually is using the motor exhaust as its cooling airflow. So that's a pretty marginal design. The motor is something like 91, 92% efficient, and our inverter is something like 96, 97% efficient. So all of that heat that the motor has to reject is warming up the air that comes out of the motor, and then the inverters are mounted right behind it. But we think the design will still close. We're working through some of the routing right now, but it's enough that the temperature tolerance of the inverter system is like 150 C, so it's able to tolerate quite a bit, and we're able to apply margins to that and still make the design close.
So Gabriel asks, what is the minimum number of motors that you would need to keep the airplane aloft in typical weather conditions?
Yeah, that's an interesting question, and it's really important for the way we design the X-plane, basically. So one answer could be zero. We've designed this airplane with a lot of experimental technologies, and we know that the technologies itself are immature and may fail. And so that's one of the advantages of flying out at Edwards Air Force Base is we've got really long runways, and if we have a problem getting to a runway, we've got huge dry lake beds that we can use as emergency landing locations. And so that's a critical safety feature. But if you want to maintain level flight or even have a bit of a climb, we're able to do that with certainly 3 out of the 4 cruise inverters working, 1.5 cruise motors working well. Probably we can do that with even less. We can definitely do it with losing an entire battery. So we've got our battery split up into 2 banks, and if we shut down a battery, half the power to each wing goes away, basically. And we're able to have controlled flight, much lower performance, but we're able to fly back to the runway from anywhere we'd be in the pattern there as well. So it gets really complicated when you've got 14 motors, because all the different combinations that could fail is a lot of analysis. But we're going through that and using the flight simulator to help understand that as well.
So I think we've got time for one last one. You showed a picture of some of the flight instruments that you all are working in the design of those. The question was, would there be any, would those need to be qualified outside of NASA before you begin operational flight test?
We don't have to, because NASA has a very robust airworthiness process. So we're actually using, those displays are actually automotive. They're used in the racing industry. But it's nice because we're able to quickly mock up new widgets and get them in front of the pilot. So it's kind of a simple starter glass cockpit for our analog airplane. But we're also taking them through a full flight qualification program. So we put them in our thermal and vibration chambers. We took them up to altitude. We do all of the isolation and functional testing, and we do pretty robust software testing as well. So because we've got those programs in place, we're able to cherry pick technologies that aren't already intended for aircraft.
That's great. Thank you so much, Sean. I apologize. I think there are about 3 of you whose question we didn't get to, but we're going to go ahead and wrap this up. Sean, I want to really take time out. It's obvious you all are busy. It's obvious you got a lot going on, and I certainly do appreciate you taking time out to do this. We're very grateful, and I think it was a very, very informative brief for all our listeners. Thanks to everybody for joining us today. So as I mentioned at the beginning of the webinar, the slides and recording of this presentation will be made available for download at www.hdiac.org. If you're interested in learning more about the HDIAC or getting involved as a subject matter expert, presenter, or expanding your presence in our user community, please feel free to reach out directly, and you can use the contact information that you're going to see on the left-hand side of the screen. In addition to these monthly webinars that we try to do a couple times a month, the HDIAC also offers monthly podcasts that span the range of our 8 technical focus areas. We kick out a bi-weekly email digest with the latest scientific and technical news in the Homeland Defense community. And we also provide a technical inquiry service with up to 4 free hours of technical consulting. So ask a question and we'll work with our subject matter experts and our staff to get you an answer. If you're active in the Homeland Defense community and are interested in joining our subject matter expert community, please reach out directly. Again, we cover 8 technical focus areas. There's a lot of good information out there. And our subject matter experts contribute in a variety of ways, including presenting webinars like what you've seen today, providing podcasts, and providing consulting as needed to respond to any of these technical inquiries that our core staff can't answer. So our contact information is included in the chat box on the left-hand side of the screen. And then be sure to join us 30 April for our next webinar, and that's going to be covering radiation response given by the Guardian Centers of Georgia. If you register as a member on our website, you can subscribe to receive notifications of the webinars and the podcasts such as you've seen today. So again, Sean, thank you very much. Thanks to everybody for their time today, and best regards, and stay well.